Dear students, welcome to our class on JRF SRF Net 2022 Agricultural Meteorology Advances 3. Here, I would like to impress upon you that in the advances, we the agricultural meteorology students, okay, and teaching staff should know the fluxes. Okay, what are the fluxes? Number one is moment of flux. Okay, the fluid flux, in other words, it is explained by Newton's law of viscosity. Second one, mass flux. So what is mass flux? Mass flux is movement of mass from one state to other state. It is explained by Fick's law of diffusion. Third one is the heat flux or energy flux. So heat flux or energy flux is explained by Fourier's law of thermal diffusivity or thermal conductivity. Why diffusivity? Why conductivity? I have explained to you. In general, if a body is there, from that body, how much internal energy is conveyed to a fluid, okay, in the form of conduction. Once again I repeat, how much energy is there in a particular body, okay, that particular energy when it is conveyed to a fluid, say for example a 1 acre paddy field is there. From that paddy field, how much energy which is available in that paddy field is conveyed to the air, which is a fluid. That's what we call it as the mass, okay, flux. Another example is if a pond is there, from the pond evaporation goes on. That also we call it as the mass flux. In other words, precipitation in the atmosphere. So that also we call it as the mass flow or mass flux. Flux means rate, okay? Flux, okay? Both are, flux is equal to flow, but when we give a rate, we call it as the flux, to be very precise. So here, the third one is the heat flux and heat conductivity. And again, once again, Newton's law of viscosity explains the moment of flux. Fick's law of diffusion explains the mass flux. This Fourier's law of diffusivity or Fourier's law of conductivity. Why diffusivity? Why conductivity? I have explained to you in the micrometeorology. Please study. Subscribe to our channel, Agrometeorology, Farmers and Rural Development. There I have given. Now, here, just after giving some important bits for your JRF, SRF, I try to explain those fluxes in terms of coefficients, dimensionless numbers. So Reynolds number, Richardson number, Saspedit number, and Nusselt number. These are all very, very interesting, absolutely interesting. Those things also in the form of bits we try to understand. I also try to explain to you. Now, see here, for example, let us see what is heat capacity, fundamental, let us see the heat capacity and its application. Application comes under the advances, heat capacity application. Let us see. Now, because of which the sandy soils warm up more rapidly than clay soils, for example. This is the question given to you. What is the question? Because of which meteorological factor, or because of which law, because of which you can say process, heat, when the sandy soils become warmed up, or they become very, very, very quickly warmed up as compared to clay soils. Now, the answer is because of the lower heat capacity or lower heat, you can say thermal capacity, and poor thermal conductivity. Two things are there because of low thermal capacity. Because of low thermal conductivity, sandy soils become more warmer as compared to clay soils. And the same thing, the energy received by sandy soils, the energy received by sandy soils is concentrated mainly in a thin layer. It is the energy received by the sandy soil is confined to a very thin layer because the thermal conductivity or thermal diffusivity is low for the sandy soils as compared to clay soils. Okay. There is an extraordinary rise in the sandy soils because of these two. Because of those two? Thermal conductivity, before that thermal capacity or heat capacity. So here is the beginning for advances that you should know. This can be very well explained by Fourier's law of thermal diffusivity or conductivity. So like this. Now let us see what is the specific heat. Even though this is an advanced course, what is specific heat? The heat capacity of a substance in relation to water. See, 15 degrees centigrade is there. We are raising it to 1 degree centigrade. So how much heat energy is required? That's what we call it as the thermal capacity. So thermal specific heat means how much energy is required as compared to or in relation to water. We call it as the heat capacity. Here the practical application, let us see. If we add organic matter to the soil, the questions may be like this. If we add organic matter to the soil, what happens to thermal capacity and thermal conductivity or thermal diffusivity? This is a question. Now, when we add organic matter to the soil, there is a reduction in the heat capacity, and thermal conductivity. There is a reduction in the heat capacity and thermal conductivity or thermal diffusivity when soil is added with organic matter. This is the application as far as advances are concerned. So it's a PG level question, not PhD level question. PhD level question would be like this. See, in the Fourier's law of thermal conductivity, thermal or thermal diffusivity, a paddy field is there, or you can say a dry crop of say a millet crop is there. The millet crop is experiencing a drought. Now how much energy is conveyed from 1 hectare of a millet crop experiencing drought? Is it from the crop to the environment or air? That is a fluid, or fluid to the crop. Fluid means air. So in which direction it is going? Question would be like this at the SRF level, or at the PhD net level, or you can say in the interview level. There what you should say, a hectare of millet crop is there. That crop is experiencing drought. That means there is no movement of, there is no availability of water to the crop. Then what will happen when water is not there to the crop? The crop tries to protect itself by closing the guard cells. Once it closes the guard cell, again the temperature increases. From where the energy flow? From the crop field only into the atmosphere, or some advective heat is further added to the air. Then what will happen? There is a possibility for neither losing nor gaining the heat either from the fluid by the crop or from the crop to the fluid. Like that you should explain. So those things we try to understand after 2 to 3 minutes. Now let us go to thermal diffusivity. Simply the rate of change of temperature with time, we call it as the thermal diffusivity. It is an expression of the rate at which a substance heats up as a result of thermal gradient. As a result of thermal gradient, how? You see, when we are walking on the road, it is a hot sunny day. If we by mistake there is a problem with our chappals, or you can say the footwear, so then we cannot walk with the footwear. You are forced to go barefoot. Then what will happen? You get with the shoe, you are comfortable. In the absence of shoe, you feel so much uncomfortable. Why? Because your body, the thermal conductivity of your leg, which is exposed to the soil, which is very, very hot, very, very high. So, molecular movement is there. Molecular movement is very quick as compared to when you are wearing the shoe. Similar thing happens as far as crops are concerned as well. So that's why. Now, what is the application? Say, if a maize crop is there, when we give irrigation to the maize crop, what will happen? The water flows into first surface, from there to 2 centimeters, 4 centimeters, 6 centimeters, like that, it will go into the soil. There, what will happen is the soil in the maize crop, allows the heat, the energy to grow uniformly deeper into the soil as compared to a dry soil. So here what I wrote is moist soil is more uniform. When we give irrigation to the maize crop, that there is a moist soil. Moist soil is more uniform in temperature throughout its depth, as it is a better conductor of heat than the dry soil. This answer you should write. What is the question? What is the answer? Once again, for your academic interest, we discussed. What we are discussing? Thermal conductivity or thermal diffusivity. Just a half minute back, I gave an example of when we are going in the sun with shoe or without shoe. What will happen? Same thing happens here. Here, a maize crop is given water. So there is a uniform flow of heat in a maize crop where you have an irrigation as compared to a day before that there is a dry crop of maize. So if you see the heat flow, so heat flow is more uniform under the irrigated condition as compared to the dry condition. So from here if we start, let us see what are the fluxes. Flux means flow. Flux means flow. Rate we add here. Instead of flow, of course, mass flux, momentum flux, heat flux. These are all the phrases. In English, there are, the phrases. PHRASES. Phrases are there. So these are all the phrases. Different sciences, agricultural sciences, medical sciences, mathematical, whatnot, engineering sciences use the word flow, mass flow, thermal, heat flow, you can say water flow or momentum flow, what we call it as. So they use it as a phrase. Now, see what are the fluxes. Why we should understand for that, you should understand. Why agrometeorologists should understand. If not at the level of engineering student, if not at the level of an advanced medical student, why, to what extent agriculture students, particularly the meteorology students, shall know the fluxes means? See, mass flux, that is first momentum flux, Newton's law of viscosity, mass flux, fixed law of diffusion, and heat flux. Here, why we should know is, whenever you wanted to schedule the irrigation, different methods of scheduling the irrigations are there. Say particularly, for example, in my M.Sc experiment, PG experiment, I have gone for Bowen's ratio calculation. How I have gone for, I have gone one micrometeorological stand, dry bulb and wet bulb is there, different heights, logarithmic heights I have given, wind speed, anemometer I have kept it there. So like that, what are all the requirements I kept it. Fluxes I measure. So in the logarithmic wind profile, how heat is flowing, how water vapor is flowing, how this diffusion is taking place when I use the irrigation, because there is a uniform flow of heat into the soil. So in the soil heat flux, in the micrometeorological stand, how they are given. So that's why here I would like to impress upon you that over a very smooth surface, which is flat and uniform, Okay, under minimal heating or cooling conditions, uniform surface is there, minimal heating or cooling is there, then the wind speed above that surface increases as a logarithm of height above the surface. Wind speed, wind is a fluid, water is a fluid. So how, okay, a uniform surface, okay, which is exposed to either heating or cooling, influences the wind over that surface. It influences the wind in such a way that logarithm of height above the surface, the wind speed increases as a logarithm of the height. This is what I told half back with a micrometeorologist. And similarly, neutral conditions occur when the surface is in thermal equilibrium with the overlying atmosphere. Neutral conditions occur when the surface is in thermal equilibrium with the overlying surface. This bit may come. Another thing is just before sunrise and just before sunset and under the overcast, that means cloudy conditions, what happens is surface and surface air conditions are similar. When under the neutral condition, first under the neutral condition, surface is very smooth, it has got and minimal heating or cooling is there. So under three conditions, just before the sunrise, just before the sunset, and under the cloudy condition, what happens is the surface and surface area conditions are similar. Okay, as half minute before, as far as wind is concerned, the wind speed increases as a logarithm of the height over a smooth surface. Third thing is that the effective height, that's what we call the surface, effective height if a crop is there, where leaf area index is maximum, there the momentum or all the fluxes are absorbed there only. Why? Because there is a maximum leaf area index, which under those circumstances the movement of fluxes or flow of fluxes are more. Another last 1 minute I would like to share with you fluxes in the layer non-neutral conditions. Non-neutral conditions, what is that? In sunny conditions, the heating of air close to the ground by the surface causes mixing of the air. Surface is there, very hot sunny day is there, so mixing of air takes place. The air becomes less dense near the surface with cooler particles above it. Near the surface, air is so much of heat is there. Air molecules will become very very hot. That means less dense as compared to above these particular molecules of the air in the surface over the surface. Now, turbulent transfer due to mechanical turbulence is therefore enhanced by heat convection. From the surface, heat convection takes place, which increases the intensity of turbulence in the atmospheric boundary layer. These are known as unstable or convective conditions. Unstable or convective conditions are created in the atmospheric boundary layer by intense heating of the surface, where adjacent molecules become very hotter as compared to upper molecules. When heat is conveyed, energy is conveyed to upper layers, then the conditions are unstable or convective. Now here the important bits are: heat convection is the principal generator of eddy motion. Molecules differs a lot from eddies. That's what I told in the theory. Now here, heat convection from the turbulent low dense air with so much of energy. Heat convection is the physical generator of eddy motion in fully developed atmospheric boundary layer, because the generation of mechanical turbulence decreases rapidly with height as the wind shear lessens and the size of the buoyant flumes increase with height. So that means from on two conditions, very hot sunny day, surface is there, it becomes less dense because of so much of intense heat. Molecules are in an unstable condition as compared to upper. From here, when energy is conveyed, instead of air molecules, we call in terms of eddies. Eddies will become stronger, and so unstable conditions occur. What happens in the night? During the night, the surface is cooled by radiative transmission. During the night, surface gets cooled. Then, the surface air cooled by the ground and conditions of suppressed turbulence prevail. So these conditions are described as stable and are characterized by light winds. Here, light winds are there when during the night time. Why during the night time light winds are there? Because after the source of heat, sun is disappearing, energy is not there. Because of the thermal infrared radiation going into the atmosphere, the surface layer becomes cool. Once it becomes cool, the eddies will become dummy. Slowly they lose their shape. So here the stable conditions prevail because there is no turbulent exchange of heat or supply of heat by the molecules near the surface to the above atmosphere in the form of to receive in the form of eddies. In the absence of eddies, what we get is a stable atmosphere. So these are the things that I would like to discuss with you. These may come in any form, in the form of bits. Thank you very much for your very patient hearing.